Hey everybody, back for week number 4 here. Wanted to start with problem number 2. Simple 2-mark question on 2a. So let's get started. It says consider the function f of x, which is sine of p arc sine of x, and which exists here between negative 1 and 1, where p is in the real numbers. Show that the derivative of this function at x equals 0 is equal to p. So the derivative of f of x will equal, using the chain rule, cosine of p arc sine of x multiplied by the derivative of p arc sine of x, which will be p over the square root of 1 minus x squared. All right, now if I evaluate that at 0, I'm going to get cosine of p arc sine of 0. Arc sine of 0 is 0, so p times 0 is 0, times p over the square root of 1 minus 0 squared. Okay, so evaluating both of those separately, cosine of 0 is 1, and p over the square root of 1 is p. Therefore, f prime at 0 is equal to p. So that's a pretty easy 2 marks to get you started. Let's take a look at part B. The function f and its derivatives satisfy the following. This is kind of funky, but it's really no more than just a bunch of crazy notation for a bunch of derivatives. So if we take a look at this, if x equals 0, so what we want to show is that the n plus 2th derivative is equal to n squared minus p squared times the nth derivative evaluated at 0. Okay, this is a 1-mark question, you guys, so it doesn't have to be intimidating. It just has to be plug and chug. So I'm going to plug a 0 in for for x everywhere I see it. Okay. And I'll plug in a 0 here. Notice that 0 will just reduce everything out. This 0 is what I'm talking about. Plus p squared minus n squared, nth derivative at 0. And what I want to show is that the the n plus second derivative evaluated at 0 is equal to all of this stuff over here. Okay, so let's analyze this a little bit. This will be 1 times the n plus second derivative evaluated at 0. So that'll just be this. Okay, this whole term here, because of this 0, is going to disappear. Here you go. Okay, so what I have left is this, and I'm going to bring it to the other side. When I bring it to the other side, it's going to change the sign. So if I multiply that by a negative 1, that will change this to being n squared minus p squared times the nth derivative evaluated at 0. And there you go, you've got your 1 mark on part B. Now I'm guessing the 1 mark is not writing that down. The 1 mark is given for writing all this out and evaluating at 0. Okay, so with that, let's move on to 2C, which I'm guessing probably has something to do with that. Why, yes it will. It says for p in the real numbers not equal to negative 1, positive 1, negative 3, or positive 3, show that the Maclaurin series for f up to and including the 5th degree term is the following. Okay, so I'm going to go off camera for just a minute, and I'm going to come back with some information, and we'll build this polynomial. Okay, so here we are. Reminder, the function was f of x equals sine of p arc sine of x. F at 0 will equal 0. If I plug a 0 in, arcsine of 0 is 0, p times 0 is 0, sine of 0 is 0. Okay, that's why we won't see a constant term show up here in this polynomial. F prime at 0 equals p. We got that from part A. That was our answer for that 2-mark question. And then we built this in, I believe it was part B. Okay, and that's going to help us to find the third derivative based on the first derivative, right? So the n plus second derivative based on the nth derivative. So if n was a 1, this would be a 3. So let's build this real quick and find the third derivative. Okay, so the 1 plus 2 derivative of f, which is the third derivative of f, evaluated at 0, would be n squared, n being 1 squared minus p squared times the first derivative, which was n, at 0. Notice here how this 1 is n, therefore this n is 1, and this n is 1. Okay, so we're only going to be dealing with odd powers here. So the third derivative evaluated at 0 is going to be 1 minus p squared times p. Okay, so our third derivative evaluated at 0 is going to be p times 1 minus p squared. And look, this is cool. Look at that. Sweet. All right, so let's find the fifth derivative. So the 3 plus 2, which would be the fifth derivative, would be the value n, which in this case will be 3 squared minus p squared times the third derivative evaluated at 0. Okay, so that means the fifth derivative evaluated at 0 will be 9 minus p squared times the third derivative. And the third derivative, as we can see from above, was p 1 minus p squared. Okay, so the fifth derivative evaluated at 0, I'm going to write it in the order that I think it should go. Okay, and there it is. Okay, again, notice that it shows up here, so we can build the polynomial f of x approximately equal to, I could throw f of 0 in there, plus f prime at 0 times x plus f triple prime at 0 times x cubed over 3 factorial, by definition the Maclaurin series, okay, plus p 9 minus p squared, 1 minus p squared, x to the fifth over 5 factorial. Now, if these terms here are not in this order, right? Well, if you have these scrambled up, provided the parentheses are nested accurately, it does not matter if the order within each term is scrambled. However, if you put it in this form, it'll be easier for them to mark you correct and give you full marks and give you no excuse. Okay? All right, let's move on to part D. Let's see what they got in store for us. Ooh, this will be good. All right, it says hence or otherwise. So that means you can come up with a different way to evaluate this if you'd like. Okay, but what I'd notice, you could either use L'Hopital's rule here, or you could use the function that you just built, right? We could say, since we know that the numerator here is f of x, and f of x is approximately px plus p1 minus p squared x cubed over 3 factorial plus p times 9 minus p squared 1 minus p squared x to the fifth over 5 factorial. I could plug that right in there and then reduce out x's. Or I could use L'Hopital's rule, seeing that the limit of the top would be 0 and so would the limit of the bottom. I think I'll probably take the time to do both here if you'd like me to. So I'll start with the limit as x approaches 0 of f of x. I'm going to take that, p 1 minus p squared. I think this is a cool way to visualize the use of the Maclaurin in order to evaluate limits. It's not necessary. However, it would be necessary if this problem prompted you with hence. Because it says otherwise, that means you can also use L'Hopital's rule. So I'm going to take this expression all over x and take the limit of that as it goes to 0. So if I did that, okay, what would happen is this x would drop off, reducing with this x at the same time that that would reduce to a 2. That should be a 2. And at the same time that would reduce to a 4. However, what will happen, right, is you'll have p plus p 1 minus p squared x squared over 3 factorial plus p 9 minus p squared 1 minus p squared x to the 4th over 5 factorial. And this series would go on, but something cool would happen as x goes to 0. Right? These terms 0 out, and so would the terms after that. Therefore, this limit as x approaches 0 of f of x over x would head to p. That's pretty cool. Okay, so using L'Hopital's rule, if I knew that the limit as x goes to 0 of sine of p arc sine of x went to 0, and so did the limit of the denominator, that is grounds for using L'Hopital. So by L'Hopital, then the limit as x approaches 0 of sine, oh my gosh, p arc sine of x over x would be equivalent to the limit as x approaches 0 of the derivative of each of them separately. Don't use the quotient rule. That's going to hurt, and it's not correct, so don't do it. Okay. Derivative of x is 1. So if x went to 0, right, if I were to evaluate that, what I would get is the cosine of 0 times p over 1 over 1, which the cosine of 0 is 0. P over 1 is p, so, excuse me, cosine of 0 is 1, so 1 times p is p over 1. So either using L'Hopital's rule or using the polynomial and reducing, and it's kind of like a factor cancellation, we get the exact same answer. And that's it for problem number 2. So building Maclaurin, a little bit into series, a little bit just with derivatives and all that good stuff, and then a limit at the end. So if you got questions, let me know.